Let's begin. As promised, I wanted to show you a picture of a horse. But this is a very special horse. And I asked my students, what do you see when you see this horse tied up to the chair? People see different things, interestingly. Well, not surprisingly. So what do you see when you see this horse tied up to a chair? And, you know, the horse is staying there, not moving. Thanks.
Maybe you haven't figured out you can move it yet?
Okay.
Cool, soon.
Yeah, but like what's this deep subliminal message in this? Is that, you know, oftentimes the thing that's holding you back is just your perception that you're tied up, right? So, you know, from the horse's perspective, it thinks it's just tied up, but it doesn't know, if it looks a little bit further, it would recognize that this chair is nothing to the horse. It could just kind of, you know, do this and then get it out of the way. So, you know, sometimes be patient with yourself when you feel you're about to make, when you feel you're stuck and can't move. Take a breath and think about this cute horse in very low resolution that you might just be tied up to a chair, and it's just in your head. Okay. All right. So last time we did systems of ODEs, linear, nonlinear, doesn't matter. Solve IVP does the job. It's a great tool. I've already seen a couple of homework submissions for the homework assignment with the galloping Gertie, the oscillating bridge. It's a fun problem. You have all the tools to do it, and you can focus on studying and analyzing the system. And now, after that, I thought that we needed to have a talk about stiffness. We hadn't talked about stiffness yet, and it's hard to talk about this topic without getting into the weeds of numerical methods. But this class is not about numerical methods, so how the heck am I gonna try to explain that to you so that, you know, I give you enough knowledge you don't get in trouble, but the knowledge you have, you're not gonna be an expert in it. So it's a fine line teaching these methods that we're passing on to you. But this is an important topic that you need to be aware of if you're ever using things like Solve IVP or any ODE int from MATLAB or any canned ODE solver. And we will start by doing some observation together. We will look at what's called the van der Pol oscillator. This is a spring mass system, you know, like you've studied in physics. Typically, what you study in physics is that the simplest model of a spring is that it reacts to proportionally to the displacement. So you displace a spring by delta x, the restoring force is going to be a constant times delta x. But that only applies for very small displacements. Springs react linearly, k times delta x, when the displacement is small. But when displacements become larger, there is a nonlinear restoring force. Okay, and that's exactly what's happened with the bridge, with the homework problem that you're working with. When one side of the cable is in tension, it's not going to restore it by the same amount as the other side that is being compressed. So you start getting this asymmetrical imbalance in the bridge. But this is the case with more realistic systems. And one classic example is called the van der Pol oscillator. And it has a nonlinear restoring force. So if you go back to your F equal ma and you apply it to a spring and you get the acceleration, so this is mass times acceleration, you're doing the balance on the object, and this is the restoring force. Well, this is actually a damping term blended with some restoring force. This would be where you would have a kx, but anything that's multiplying a velocity, which is x dot here, is typically a damping term, like drag. So it's going to try to slow down the system from being extended or compressed. And this coefficient here is highly nonlinear because it depends on the position itself. There's a parabolic response on the position, x squared. and you have this constant coefficient, so you have x squared times dx by dt. So it's a very nonlinear spring mass damper system. It's a classic problem. They study it in nonlinear dynamics, and x here is the position, and therefore dx by dt is the velocity, and mu is just a damping coefficient. How much resistance does this oscillator have towards displacement, making it displace? So we're going to solve this together and observe some things, but first we do order reduction. So we call x, we call it u1, and now u1 is our position. And oops, I didn't update this apparently yet. And u2 is x dot, just like we did with order reduction. If you take the derivatives, now you can have our system as u1 dot is equal to u2, and u2 dot is this thing. So you have a new system of first order, two first order ODEs that we will solve with solve IVP. Okay, so we're gonna get our notebooks up and running. So if you want to get those as I get this ready, and so we want to experiment with different values of mu. Okay, we're gonna experiment with different values of mu and just plot how the position is changing. It's gonna oscillate. It's gonna have a period, and we want to plot that and observe a few things. And then the question is, what do we observe? And I'm gonna guide you through that observation. But then we're gonna change, and we're gonna change something called method in solve IVP to BDF or RADA, whatever those mean. I'm just telling you we need to change those. So get your Jupyter notebooks, and so we can study this system together. Let me quit it first. See if it updated, because I made some changes on my end. Okay, lectures. Okay, get a Jupyter notebook up and running, please. And there's more chairs over here today for some reason. All right. Give me a moment, please. So I'll create a new Python notebook. So feel free to get the boilerplate stuff. We will need solve IVP for sure. All right, so let's see, where were we over here last time? We had all of this up and running, so we'll just copy and paste this. I'll do here fall 2025. Van der Pol oscillator. Okay, let me put the equations up. I updated them in my office, but they didn't update here yet, so we're going to have some issues with some of the animations. Okay, so we will declare our Van der Pol right-hand sides, right? Because that's what we will feed to BVP, solve IVP. So we have these two right-hand sides, and then we go def, Van der Pol, and by definition we get T and Z. I'm going to call it the vector of the variables containing U1 and U2. And then I want to pass mu as an argument because I want to study this system as I change mu. So that's what's asked of us, okay? Is to study the system with different values of mu. All right, so first thing I'll do is do u1, u2 equals z. So that will unpack the two variables, and then I will return a vector of right-hand sides. The first one is u2 over here. That's corresponds to the right-hand side of u1 dot. And the second one corresponds to the right-hand side of u2 dot, and that's mu times 1 minus u1 times u1, so that's u1 squared, times u2 minus u1. Agreed? I've returned this. Perfect. And now we can start solving this. Let's see. And okay. We will do, let's set mu is equal to, let's start with mu equals 0.1, is a small number. And we will do our t-span. We're going to go from 0 to, let's maybe do 100 seconds. We're going to need more, but we'll start with 100 seconds. It might be a lot for this value of mu. We'll just explore, right? We have the tool to do this, so we can explore this. And my space, I want to define a space to plot this at, and let's do maybe 100 points or what, 200 points maybe. Let me check something here. Okay. So I'm not going to do t-space. Let's see what it does first. All right. We still need initial conditions. So my initial position, I'm going to move it 2 meters. And so IC initial condition is 2 meters. Let's just stick with that. And 0 speed, right? So these are the initial conditions. And finally, t-span is equal. Finally, solve IVP. And what do we give it? We give it the van der Pol, right-hand side. That's the right-hand side. And next, we want to give it the t-span. And then we will give it my initial conditions, the initial conditions. And then we don't forget args equal mu. So that's the mu that we defined here. This is not the same mu in here. It's a different word. I know they are named the same, but this mu over here is going to come from this value, and then will be passed on to the right-hand side over there. Okay? And it solves it. Then plt.plot sol.t. So let's do this. T is equal sol.t, and position is equal sol.y 0, right? Because we store the position in the u1 is the position, right? So we will call this t, and then position. And then if you plot this, you see plenty of oscillations going on here. Okay, not much damping. Let's reduce the t-span. Let's go to maybe 30. Let's do 30. Okay, so it looks a little bit better. It's kind of jagged, so let's create a t-space or t-eval. T-space is mp dot linspace, and I'm going to go from t-span 0, that's t0, and to t-final, to, actually let me do it better. t0 equals 0 and t-final equal 30.0. My t-span would be t0 and t-final. And here I'll go also from t0 to t-final, and let's put 100 points. And then here we would go for, we'll change this to t-eval is equal t-space, right? And then it looks a little bit better. Let's do 300 points. It looks much cleaner now. Okay, plt.grid. And okay, so on the x-axis, it's showing me time in seconds, and the y-axis displacement in unit lengths. You can think of it as meter or centimeter. It's all normalized anyway. So it starts at 2 as expected, goes down to -2, goes up and down, and it just looks like this nice classic cycle that we're all familiar with, right? Okay. So now let's go and change mu. Let's go to mu equal 1.0, see what happens. And I run this. It ran. Okay, so when you change mu, you start seeing that the curves, they start getting a little bit, they're kind of trying to move to the right, and we call this, they're starting to get a little steeper. Okay, so there's no more this smooth cycle on the way going up or on the way going down. It's trying to get sharp. It's trying to get more and more vertical. So if you compare this vertical grid line over here in gray to the line in blue, you will notice that the blue line is trying to get more and more vertical as we change mu. So let's see this better. So let's go to mu equal 5 and run this. Okay, so you see how it's getting more and more flat, more and more vertical, that vertical line, but also the number of cycles is changing. Okay, so 30 seconds is only showing me just a couple of periods, right? So if we go to 10, let's go to mu equal 10 and run it. It ran, but now it's only like barely 2 cycles in 30 seconds. So a cycle and a half, I suppose. So let's go to a little longer, maybe 100 seconds for T final. I'll still keep 300 points and mu equal 10. Okay, so it's doing this. Let's go to mu equal 30 or 20. Okay, it's still doing that. That's the pattern. Let's go to mu equal 100. Oh, do you notice what happened here? So mu equal 100, I ran it. It took like a little second to compute it. And then it's showing me only barely half a period. So I want to go for longer times now. I'm going to go to 500 seconds. And I'll put, okay, so 500 seconds. Oh, look at that. Do you notice what happened? I ran it. It's still running. And then it gave me the result. Okay, good. So now I'm at 500 seconds. Okay, let's go to mu equal 500. It's still getting more and more vertical. So let's keep pushing mu and now run this. See you tomorrow, guys. Okay, it took much longer. Let's see the solution. Okay, so now it's only barely half a period. So I want to go more time. Let's go to 1,000. Okay, and run this again. And it's taking longer. It's taking longer and longer. If it's ever going to get to a solution. And this will only probably just produce 2 periods. Okay, finally we got it. Let's see how many periods. Maybe just 1 period. We just got it for 1 period. If you want to resolve 2 periods, you can imagine, like if you want to go to 2,000, it's going to take significantly longer. Okay? So something is going on, right? Something is going on. This is not a very complicated system. This is we solve systems of thousands of equations like this, and we want to be able to get the solution rather quickly than having to wait for this, because this could not be the only thing that you're dealing with. This could be just only one piece of a much larger system that is going to take even more time to solve. And so if this becomes the bottleneck in your calculation, this is a problem. It's taking too long of a time, right? And it's only barely got us a couple of periods. Okay, now you can imagine what happens if I go to mu equal 1,000. It's going to get much slower, right? Okay, so there's something going on here with mu. As I increase mu, the solver takes longer and longer. Remember, last time I mentioned something over here. It's called, what is it? I told you, remember this, NFEV, number of function evaluations of the right-hand side. Okay? So I want to see what's going on. I'm going to ask solution to give me, so sol.nfev. Now, if I print that, it did 3,730,000 function evaluations to only cover 2 periods of the solver. What's a function evaluation? It's calling back that van der Pol system over and over and over again to calculate a number, to calculate something. Okay, whereas I'm only plotting it for what? 300 points. Agreed? So ideally, I only want 300 function evaluations. Why is it giving me that many evaluations? So let's go back to smaller mu then. Let's go to 0.1. Okay. Okay, so at 0.1, I have 18,158, 0.01. Okay, it's 12,000. It's much less as we shrink mu. It's much, much less number of, it's still high, 12,000, but it's pretty fast, right? So there are 2 measures we're going to look at here. Obviously, the time it takes to compute, to solve the system, and the number of function evaluations. They're going to be consistent with each other. The more function evaluations you need is going to correlate very strongly with with the time it takes to solve the problem. There's a great little tool built in Python. It's called performance counter. It doesn't count the time on your clock or the wall time. It counts the time the CPU actually just spent on doing the solution. Because your CPU is trying to solve this, but at the same time trying to check your TikTok messages or whatever, Instagram messages, trying to pull email, etc. It's doing a lot of other things. We only want to measure the time spent computing this. So you call what's called a performance timer. All right, so let's pull that in. We're going to import. To do this, you do import time. So this is a really great library to do performance benchmarks for your code. Okay, and we will do tick. We say time dot performance counter, and then talk equal time dot performance counter, and then your total time would be, so that's tick is the beginning time, and talk is the end time, and then elapsed time is equal talk minus tick, and then print elapsed time. That's going to be in seconds. Okay, elapsed time in seconds. So if we run it, this is 0.2 seconds it took. As we increase mu, it's going to get more and more. 0.2, still 0.2. Okay, 0.5 seconds it took. And then we can also do the number of function evaluations. Print or seconds with sol.number function evaluations, function evals. Okay? It was 44,000 function evaluations. Mu is equal 10. It took almost 1 second. Mu equal 100. Let's see, it took 7.5 seconds and so on. So that's a lot. 7 seconds. If you're solving just this system, that's not a problem. But what if I want to run it for 5,000 seconds or 20,000 seconds? It's going to take you an hour to get this sorted out. Okay, there's a problem here. So let's do something even better. Let's actually run this for a bunch of values of mu. Okay. So for a bunch of values of mu and measure the performance. Okay, I'm going to do muse is equal to np.linspace. See how I did it here. So we're going to go from np.linspace. We'll go from 0.1 to let's say 200. Mu equal 200. I don't want this to take forever. I will do 40 values of mu, and for each value, I want to measure the time, store it, and then plot it to look at my performance. Agreed? Okay, and so I am gonna count the time elapsed time. It's an empty array. I'm going to put the times in it to do this. And because this is going to scale correctly with the time, so I don't have to run it for 2,000 seconds. I can get an idea of what's going on even if I run it for 100 seconds or 500 seconds. We can keep 2,000 seconds if you want. That's OK. And so for mu in mu's, so for each mu now, I'm going to repeat this over and over again. So I copied this from here and put it here. Tick, solve, etc. T space, args is mu. Then talk, elapsed time. Don't print it now anymore. And then let's call this elapsed times. And then elapsed times dot append elapsed time. Okay. And so I think that should be it. And once we're done, so let me do this here for 1,000 seconds. Okay. And just to be consistent here, I'm going to copy and paste these over here. So this stands on its own merit. I'm going to run it. It's going to take a minute. And next, I'm going to plot. So when this is done, I want to plot the elapsed time versus the value of mu. Agreed? Because I'm expecting either linear or exponential increase in cost. And so on the x-axis, I want to put my mu's. And on the y-axis, my elapsed times. And I'm going to do this. So we'll give this probably a couple of minutes. TF was pretty high for this problem, but that's OK. I want to make sure that you're convinced that this is costly. It's really costly. Typically, the cost should be flat or decrease. Something is going on here with this mu. We're going to look at it in a minute once we go back to the slides. But something is up with mu. As mu is increased, it's affecting the cost of the solver. Why? What is the solver having to deal with as mu is changing? Okay. Let me actually interrupt this. It's taking too long. I'm going to do this for 100 seconds. Okay. Okay. Just 100, so it's a little faster. But it still takes a long time. OK, it's done. So let's plot it. And if we plot this, you see this almost linear increase. I want to say it might turn into exponential as memory resources start getting consumed. But it's really somewhat of a linear increase. So as we change mu on the x-axis, so is the time to integrate this for 100 seconds. Now, you could do it. You could run it for 1 second and estimate what it takes as for multiples of 1 second. OK, so that's a problem. That's a problem. That's not good. The cost should be flat or actually go down for an algorithm to be appropriate. It's linear. That's OK, but nobody wants to wait forever to solve this problem. Now in the slides, I tell you do something as you make these observations. And the thing is, change the method now to BDF or DAO or something else. OK, so let's come back here where we were experimenting with this. And I'm going to start from the end. I'm going to start for mu equal 100, which took us 7, what? OK, so let's run this again how it was previously with the standard method. So for mu equal 100 and 1,000 seconds, it took almost 4 seconds to solve with, remember this, 380,000 evaluations. OK? Now do this. Go here. So we remember this. Okay, I'm gonna copy it and paste it here. Put it in a comment. Okay, so that was with the standard method. Now go and type method equal and put BDF. Just put that and run it. Whew. 0.37 seconds. Almost 1 order of magnitude less. A little bit more. 1 order of magnitude less. It's 10 times cheaper. And only 5,000 function evaluations, 5,500. Remember, this was the conventional method, the standard method in the algorithm. Okay? 380,000 function evaluations, 4 seconds. When I put BDF, it went to 0.37 seconds with 5,000 function evaluations. Okay? We can try the other methods. There's another one called Radau. Run it. Even better, 0.26 seconds with 8,000 function evaluations. I like this. I want this. Okay, what happens if I increase mu? I'm going to go mu 200 or 300. Do you think the time is going to go up, stay flat, or go down? Go up a little bit? Go up a little bit? What do you think I want?
Flat or less?
Flat. Okay, I want it to be flat or go down. Okay, now there is noise, so going up a little bit is going to be hard to identify, but let's say 10%. If it goes up by 10%, we say that's beyond noise. Okay, so let's run this. I increased mu from 100 to 300, so 3 times mu. 0.12. You were all wrong. It went down. I was wrong too when I first tried this because I didn't know the Radau was so effective at this. Okay, let's try BDF. So BDF was 0.37. Oh, look at that. It even went down more than Radau went down. So something is going on. Okay, so let's go back to smaller mu. Mu equal 10. What do you think is going to happen? I'm confusing the heck out of you. Go up? Okay, so we're like kind of going backwards, right? Okay, good intuition. Oh, look at that. 1.3 seconds. That's insane. That's weird. It's like these methods are better for larger mu, but perform worse for lower mu, compared to the conventional method, which does a better job at smaller mu, but worse job at higher mu. Okay, so let's plot this. I'm going to run this here again. But this time, let's copy this and paste it. And now we're going to do another one. We'll call it elapsed times. Let's try BDF. Okay? So we'll do BDF. Elapsed time BDF, elapsed time BDF. And here I'm going to put method is equal to BDF. Okay? And let's put this at 10 seconds. It will be the same trend, I promise you. So you agree with me that the end time shouldn't matter. It's not going to matter. The cost is going to be the same. Okay, so we'll do this 10 seconds so it doesn't take us forever to plot to be done with this. So now I'm running the same thing as I did before, and I'm going to plot. So this one was label is equal standard method, or the method in the CAN. And this one elapsed times BDF for BDF, and I'm going to do it in red. Okay, let's do Radau. What do you think? Let's do Radau as well, since we're at it. Let's do Radau. Radau. Okay. Okay, and here we put Radau. Radau and BDF are going to be consistent in the sense that, let's do it in blue, that they're of the same order. Radau, and we'll put plt.grid, and then plt.legend. Did I run this? Okay, so let's run this. Okay, let's plot. Oh, wow. Look at that. I can't even see. It's so high for the standard method. I cannot even see what's going on over here. But just from this vantage point, you see that, so Radau and BDF, they're on top of each other. Okay, so they perform similarly. There's red under the blue. Okay, and you see for small values of mu, both Radau and BDF cost more than the standard method. But then there's a point after which these they separate. Okay, so we can do this. We can try to do semi-log y, okay, or do a log-log. Let's do a log-log plot. See if it does anything for us. It didn't show much. Okay, so I'm going to switch, go back, and then plt.x limit. I'm going to go from 0 to, let me see what I did here. Okay, I'm going to go from 0 to maybe 20 for mu, so that I can kind of close off the axis. Not looking very good. Let's do 30. Okay, and then plt.y limit. Let's go from y limit. Let's go from 0 to 0.02. Okay. Okay. So you see here that there's a point just around this point for mu where BDF and Radau start costing less than the conventional method, whereas the conventional method continues going up and up. Okay? Continues going up and up. Now we can do this even a little bit better. We need to run these methods so that they achieve the same relative error. Okay, and so there's a setting that you would need to put in solve IVP so we can compare them apples to apples, because we want them to achieve the same relative tolerance. You can set that, but that's not the point. The idea here, we will get the same behavior. It will just look a little bit better. Okay, so if you see, so I do this on my code where I set the relative tolerance, and I'll show you what I'm doing here. Okay, so here, see, I'm doing these methods and I'm setting the relative tolerance, so they're both running at the same error, and you see this trend. The red is the BDF, and this is a semi-log y, and the black is the cost. Actually, let's try the semi-log y. I think that's the answer here. Let's just do semi-log y. Semi-log. So we're only doing log on the y-axis. Okay, perfect. That's much better. Yeah, so you see the BDF and Radau, they're more costly at small mu, but then after like mu equal 15, they become cheaper and almost flat. They're just gonna same cost across for all mu's. And that's what you want from an algorithm. Now, theoretically, what the heck is going on? Unfortunately, I cannot go into the details numerically. This is a purely numerical issue that comes from a physical thing happening because of the nonlinearity of the damping force, okay, of the damping, this damping term. But it's a purely numerical artifact, the cost of solving these. And unfortunately, I cannot go into the detail. It will probably take me 2 lectures. I have to learn about time integration methods and eigenvalue analysis on those to see what's going on. But roughly, we can still understand this just by qualitatively, we can understand this. So let's summarize our observation. For the standard solver, as mu increases, so does the computational time and the number of function evaluations. For the other methods, BDF, Radau, there's another method called LSODA. I'll talk about it a little bit later. We observe an inverse relation with mu. For small mu, the standard integrator seems to be more efficient. That's the key word here. But for large mu, the alternative integrators are much more efficient. BDF, Radau, and LSODA. So let's see what's going on. Here I have an animation of, notice I'm going to change, I'm running this for 2 periods exactly, so I can compute the period numerically, and I run it only for 2 periods. As mu is increased, so does the period time. So, as mu, for mu 100, 1 period is about 1,000 seconds. So I need to run it for 2 periods, but I want you to see what's happening as mu is changed. I'm starting with mu equal 0.001. This looks like a standard linear oscillator. And then I'm going to run it. As mu is changed, you'll see this shape develop. And by mu equal 1,000, 2 periods like 3,000 seconds just to do 2 oscillations. But notice what's going on. There's like the scale on the x-axis is so large. Okay, the scale on the x-axis is so large. Now, observe this. For small mu, so keep an eye on the x-axis as well. For small mu, the change in position over time, or the rate of change, the change in position over time is consistent anywhere you find yourself. So if you stand here, it's kind of roughly the same. And you come over here, there's an inflection point. It's not going any faster. Like anywhere you are on this curve, you're going about the same order speed if you want, or you're traversing that trajectory at the same rate. It looks similar, right? There's no region where things are changing faster than other regions. But as you change mu, so this is mu almost 3, you start seeing this, what we call wave steepening or flattening of the cycle, where you could start telling that there's more gradual descent over here than here. It's like you're going a roller coaster. You go up, 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 and then you go slowly, and then you go down really fast. Okay, so mu is doing this to the system. Mu is causing this in the system. And as you push mu even further, that becomes more prominent, where you have a very slow change. Look at this change over here. It's happening over about maybe almost 1,000 seconds. You're moving very gradually over 1,000 seconds, but then you drop within, guess what this number is going to be? I'll show you this number. Within a second, even less than a second. Okay? So you move gradually, like anything's going to happen. It's going to take us 1,000 seconds to do something. It's like it's the worst roller coaster ever. And then you drop down in a second, right? Okay, so these are regions of gradual change and rapid change. These are called, in this problem, because the x-axis is time, these are called the time scales of the system. Okay? There are 2 predominant time scales in this system. The slow time scale, which is this one, we call the gradual, and it's actually about 1,000 seconds. You can calculate that for this problem. And the rapid time scale at this mu, it's about 1 over mu. Okay, it's 0.001 seconds. Okay? There might be some time scales in between. They don't matter. What matters are the slowest and the fastest time scale in any problem. You'll have 2 time scales, the slowest and the fastest, and anything in between. It's having these 2 is actually going to cause a lot of inefficiency in a standard ODE solver. So if you take the ratio of these 2 time scales, so tau fast over tau slow, so we said 1,000 over 10 to the minus 3, you get a ratio of 10 to the 6. This is a dimensionless number. It's an absolute number. Okay? It's not relative. This is an absolute number. 10 to the 6 is a large number. Not compared to, it's a dimensionless number. Okay? It's not compared to anything across all time scales. If you have similar time scales, the ratio will be 1. Or sometimes the ratio is 10. Right? 10 to the 6 is a very large number, and we say the system is stiff because there are 2 very separate time scales. If you go to smaller values of mu, there's only one time scale. There's only just one time scale. It's about 1 second, and that's it. There's no separation of time scales. That's problematic. Okay, so now why is this problematic for ODE solvers? For two reasons. Because of what we call stability and efficiency. And that's it's a challenge. It's challenging to teach this without going into the details of numerical methods. For those who are taking Professor Sutherland's class, you will learn about this a little bit more. If you took my numerical methods, we might have touched on it very, very simply, but I'm going to try to explain this from a qualitative perspective. What matters in an ODE solver, like solve IVP or ODE int in MATLAB, or any numerical method is stability. We want the method to produce a solution. An unstable method will go bonanza. It will produce junk. Okay, so any good, robust solver needs to maintain stability, but also we want it to be efficient. Okay, so stability is good, let's say, to get results, but eventually you also want it to be efficient so that it gives you the solution in a reasonable amount of time. In general, there are two approaches to solve an ODE numerically. There are just two approaches to solve an ODE numerically. Methods that we call explicit and methods that we call implicit. In explicit methods, so what we're doing, we're trying to approximate the time derivative and convert it to an algebraic relation, just like we did with the heat equation. It's a little bit more involved with time integrators. But just like we did there, without going into too much detail, the way you approximate that derivative can be explicit, where you only use information from the past to predict the future. Implicit methods, you use information from the past and information from the future to predict the future. Okay? How can you do that? Well, it's in the name. It becomes an implicit equation. And an implicit equation is a nonlinear equation. So here you're solving nonlinear equations. Here you're solving linear equations without getting into much detail. Roughly speaking, explicit methods, if you are now, because this is time, it's not location, so you are now, you're not here, you're now. So you are at phi n, you have information from the past, your initial condition, or every previous time step that you calculated. To predict your purpose, you have all of this information, and you already know this value here. You want to predict the future. So you use all the information that's available to you to predict the future. The problem with this method, the advantage of this method, it's very simple. It always results in linear systems of equations that are easy to solve, but it's like driving and only looking in the rear view mirror. Right? You're not looking ahead. You're only looking at the past. And you're saying, okay, I'm going to predict my next turn based on what I saw in the rear view. Don't try this at home. Okay, maybe in like an empty parking lot, but it's a bad idea. Okay? Whereas implicit methods, they use information from the past, but you see this loop here. We're also trying to use, actually this should loop and go back over here. We're also using information from the future. They become implicit because then on the left-hand side you have phi n plus 1, and on the right-hand side you're going to have phi n plus 1, and they could be a nonlinear system of equations. They're much more expensive to solve, but they are more efficient and robust. Okay? So in general, look at this when you're trying to choose a solver. First row over here is we just expressed that. Explicit methods use information from the past. Implicit methods use information from the past and the future. Cost. Explicit methods result in simple algebraic equations with straightforward evaluations. Implicit methods result in nonlinear systems of equations that you have to solve. They are more costly than linear systems because internally they have to iterate and do their thing. For non-stiff systems, so that's when what? When the time scales are of the same order. It doesn't matter if both time scales are fast, as long as there's no separation of time scales. So you could tell me, oh, I have a system, my time scale, it's a reaction mechanism. My time scales are 10 to the minus 6 and 0.5, 10 to the minus 6. That's really fast. Is this system stiff? No. it's not stiff because you only have one time scale, it's 10 to the minus 6 seconds. But if you come and say, I have a system, I have reactions going on at 10 to the minus 6 seconds, and then airflow going on at 10 seconds to move like one thing, that's 10 over 10 to the, that's a 10 to the 7 separation of time scales. That's a very stiff system. So you don't look at the absolute value of the time, each time scale separately, it's their ratio. How far away are they from each other? And this is not only in time, but could be also in space. Why is turbulence problematic? Why is turbulence so hard to solve? Because we have an infinite range of time scale, length scales. The scale of the entire, take the atmosphere for example, the scale of the entire atmospheric boundary layer, which could be a couple of kilometers high, and the small scale of the little eddy that's spinning next to your hand, that's a sub-millimeter scale or a millimeter scale. Kilometer to millimeter, that's a 10 to the 6, 10 to the 7 separation scale. Okay? So it's that ratio of scales that matters. The absolute value of the scale, time or space, does not matter. Okay? You could have very fast systems or very slow systems. If the time scales are consistent with each other, it's a non-stiff system. What do you use for non-stiff systems? This is the method of choice, explicit methods. So when mu was small, the standard method in solve IVP is an explicit method. It's called the Runke-Kutta 45 method. It's a standard explicit method. It works so well for non-stiff systems. That's why it was faster at the smaller mu, because at smaller mu's, the time scales were about the same order. There was no separation between them. For non-stiff systems, you don't use implicit methods. There's no need for it, because they're going to be more costly. You're solving nonlinear systems of equations, whereas you can solve at the much cheaper and get the same accuracy. For stiff systems, however, when you start seeing that separation of time or length scales, explicit methods become incredibly inefficient. Why do they become inefficient? Because of stability. The solver is trying to be stable. And you see that rapid descent. In regions where you have gradual descent, you can take 4 time steps. In the region of steep descent, you have to take 100,000 points just for it to be stable. Then the solver, what it's trying to do, is going to put 100,000 points here, there, and everywhere. You end up with hundreds of millions of more points. It becomes very inefficient. You have to step very, very, very. You have to go faster than the fastest time scale to resolve the system. And that's the problem. So you end up paying the cost of the fast time scale and end up spending the cost on the slow time scale. So they become inefficient because they want to stay stable. If you take a time step larger than the fastest time scale, you become unstable. Implicit systems don't care about that. They can jump over, so that entire steep descent, it could take one time step over that and solve it and stay stable, because they have a property called unconditional stability in this here. So stability, explicit systems are conditionally stable. Your time step is limited, your time step size, how much you can go in time at any instant to solve the system, is limited by the fastest. You cannot go faster than the fastest time scale. Implicit methods don't have that problem. I can go whatever time step I want. I am unconditionally stable. Okay? So they are much more stable than, they are generally stable than compared to explicit methods, but they work very well for stiff systems. Now, does any problem have a mu? Yes, mu is gonna be similar when in fluid mechanics, the Reynolds number is the equivalent of mu. For large Reynolds numbers, you have more turbulence. So you have a stiff situation. You have very small structures, very small things that are spinning fast as well, faster than the large structures, right? And so the Reynolds number is the equivalent. Now there could be multiple of these parameters, such that based on that value, your system could land in stiff land or in non-stiff land. Okay? So that's what I want to say about this. Now, how can you tell in practice, you will know the system, you will know your domain, you will know your field. Or you start observing something weird, like just by running these scout calculations. Okay, we ran the van der Pol, we explored it a little bit, run for a little bit, for a few seconds. It's costing a lot. You see cost is coming up. It's probably becoming inefficient. And then you plot and you see, okay, there's like these crazy time scales going on, right? And so I probably should use an implicit method, okay? So the methods here, the default method is the RK45. So this is directly from the API for the Solve IVP. The standard method is Rangakata, fourth order, RK45. It improves the error by using a fourth and fifth order method, but it's a fourth order method, means whatever that means. It's an explicit Rangakata method. The error is controlled assuming accuracy of the fourth order method, etc., etc. And then you forget these 23 or this DOP and look at Radau, BDF, or LSODA. All of these are implicit methods. Radau is an implicit Rangakata method, and you can look at the references or read more about this. BDF is the standard backward difference method, like a first or second order or third order. BDF method, apparently it does anywhere from first to fifth order, and so it's trying to use more than one point in time, and in backward in time and forward in time, so to estimate the future. And the LSODA is another method. It's a blend of Adams methods and BDF. So these get into the nuances of numerical methods. Don't worry about that. Know what's important for you to know as a non-numerical person, as an engineer who wants to solve realistic problems, is to realize when you should use an explicit method and when you should use an implicit method. Know the pros and cons, know what stiffness is going to mean to you, and when to make the right choice for these guys, okay? I would always start with the default method and then see if it starts failing, if I explore the system a little bit, and if I know more about the system, then I should be able to tell. This is another problem here where this is the decay, an exponential decay. I have a very fast time scale here and very slow time scale here. And the ratio is significant, and so this is a stiff system. As well, I would use an implicit method for a problem like this. Okay. There are some additional options for Solve IVP that I want to talk about. And so I'm glad we're done with that stiffness discussion. I want to talk about a couple of additional options for Solve IVP. Hold on, let me see what I wanted to talk about. Okay. Okay, two things for additional options for Solve IVP. The first one is there's an option called events. And events is a really cool property in Solve IVP that was introduced recently with this new Solve IVP. And it allows you to detect things that are happening in your ODE solution. So for example, you're looking at reaction chemistry and you want to detect the time when your solvent reaches a certain concentration value. You're solving for concentrations. Or you're looking at a parachutist falling in the air and then you want to detect the time when they reach a certain speed or when they hit the ground, right? So what do you do with this? And you typically would just solve the entire problem and then go back and like numerically try to see where you cross the zero ground or that velocity, maybe do a nonlinear solver, etc. Turns out that Solve IVP allows you to do that automatically within it, okay? And it's a very useful feature. It has a lot of options to it, and so let's look through this. It's a callable or list of callables events. So you can have one or more events, okay? And the solver is going to stop at the first event that occurs. Okay, now you can design so it will be an event 1 or event 2 or event 3, etc. You cannot have event 1 and event 2 because they might not happen together, right? So, I might look for the parachutist when they reach 30 meters per second and hit the ground. That's not going to happen in general, right? So if you throw them from 100 meters off the ground, they won't reach that speed. So it's an or, event 1, or event 2, or event 3, etc. Now, if you integrate for a long period of time, you could probably hit all of those events, and then you will know that, okay, event 1 occurred at t equal this much, event 2 occurred at t equal that much. Okay. Now, what it does, each function must have the signature event t comma y and return a float. The solver will find an accurate value of t at which the event equal to 0 using a root finding algorithm. So this is technically a nonlinear solver. And so event is nothing more than the residual form of your event. Okay? So if I'm trying to find the time at which the speed of the parachutist reaches 30 meters per second, my event is v minus 30 because it's going to solve event equals 0. So v minus 30 equals 0 means v equals 30, right? Or I wanted to see when the parachutist hits the ground. So I need to look at z equals 0, for example, or z equal minus 400. Say we threw from 400 meters and we have the axis in the opposite direction. Then you'd put z plus 400 equal to 0. That means z equal, so you put this in residual form. The solver looks for a sign change over each step, etc. This is how it does it. Now, every event, by definition, has two options. Event.terminal, it's a Boolean, so true or false, whether you terminate the integration when this event occurs. So say, I want to integrate for the parachutist. I dropped the parachutist. The parachutist jumped from, what's it, 10 kilometers, yeah, right? They're just using, I don't know, where does anyone do, come on. Does anyone do paragliding or anything like this? So let's say, they jump from 1,000 meters, okay? And they're falling down, and you want, you're like, I don't know when they're gonna hit the ground. So you could say, okay, I'm gonna run the integrator for 500 minutes. That's a long time. Okay, the integrator is gonna go, hit the ground, and keep going. But if you say, once you hit the ground, stop, it will stop the integrator. Even if your t event is smaller than t final, it will stop. Terminal yes, stop. Terminal false, keep going. What if there's another event I want to detect? Okay, so then I would put terminal as no. Direction, this is an interesting one. This is the direction of zero crossing. This is useful in cyclical problems. So it detects, it tries to find, you tell it, okay, find the 0 on your way up or on your way down. So assume you're going through a cycle and you want to hit here. You go through here and then you go back. I want this value. I want you to stop here. So hit it on the way down. That would be -1. Direction is -1. Going up would be direction +1. If you want to detect both or all of them, direction is 0. Okay? So that's how I detected how many periods with the Van der Pol oscillator. Do you have a question? No. Okay, I was just adjusting the weather. Thank you. Yeah. So I'll show you just real quick here from mine. So how did I detect how many periods I need to run here? Okay, how many periods I need to run? Okay. All right. See, here I'm defining my event when I hit I hit 1.95, so that's 2, and then pick it up on downward crossings. Okay, downward crossings. And then how many times do I hit it? I hit it 3 times, so that will give me 2 periods. Anyway, we'll do an example. Let's do an example. So we're going to work with this example. This should have been different here. Okay, so forget this for a minute. At t equals 0, a skydiver starting at z equals 0 jumps off an airplane. Hold on, I think I changed the governing equations. Give me a minute. 1 second, please. Okay, so this one would be, with the x-axis pointing up. So at z equal, let's say 1,000 meters. Okay, jumps off an airplane and starts falling to Earth. Find the diver's position and speed as a function of time. Okay, etc. So this is the system of equations with drag, with linear drag. So we have the gravitational force. So summation of forces equal ma, and so you have the weight. And you have the drag force pointing in the opposite direction of the speed. So you have, this is a drag coefficient times dz by dt. Initially, we are at z0, which is 1,000 meters, and our initial speed, they just are pushed out, so they're not jumping at any speed. So initial speed is 0. And then you can do order reduction, and you have a system of two first order. z1 prime is equal to z2, and z2 prime is minus g minus. So this should be not squared over here, okay? And with these initials, so this is the system we're solving. And so some of our events are going to be, when do I hit the ground? When does z equal to 0? Okay, or let's say, when is my velocity minus 30 meters per second? Because I'm dropping down, the x-axis is pointing upward. So we're going to work on this together. Let me create a new. You can do a lot with events, so this is just barely touching the surface. But I want you to know that it's there. And anytime you want to detect something happening in your calculation, don't forget about events. Okay. Okay. So open up a new notebook. We have 10 minutes to do this. This is good. Okay, so fall 2025, parachutist falling events. Come on. Okay, so we will get our boilerplate from whichever one we want. Let me close this. From this guy. Okay, and let's start defining our system of equations. Def parachutist. I'm just picking up numbers over here. System and t and z. Z is an array of two variables, z1 and z2. z1 is position, and z2 is z1 dot, which is speed. So we'll do z1, z2 is equal to z, so that unpacks those two. And let's define some constants. G is 9.81, and C drag coefficient is 12.5. Mass of the parachutist 68.68 kilograms. Okay, mass of parachutist, and then return z2, and then minus g minus let's see, c over m times z2. Correct? Okay. So now let's say initial condition is we're dropping the parachutist from 1,000 meters with an initial speed of 0. And my initial time is 0. And my T final is, I don't know, maybe 200 seconds. I don't know how long it's going to take for the parachutist to hit the ground. And then we do sol equals solve IVP and parachutist system. And then our T-span is T0 and TF. So notice every time I use T-span differently, just to spice things up. My initial condition, and let's run this. plt.plot sol.t, and then sol.y 0, so that would be position. Okay, and then plt.grid. Okay, so you run the integrator, it went minus 8,000 underground. Obviously, that's unphysical, right? It's going to stop at z equals 0. So that's a very long integration time. Okay, that's a very long integration time. So let's see when the parachutist hits the ground. I'm going to define an event. We'll define an event and define hit ground event, and it's of the same signature, TZ, okay? And we'll also unpack Z1, Z2 is equal to Z. Okay, so when do we hit the ground? When Z1 is equal to 0. When position is equal to 0. So in residual form, it's Z1 minus 0, or simply Z1. Okay? So think of it this way. What is my event? Z1 equal 0. Okay? Then my residual form is Z1 minus 0, which is just Z1. So let's say when they hit 500. Okay, let's say when they hit 500. When they hit 500. Okay? So then Z1 is equal to 500, right? The residual form is Z1 minus 500. So what do I return here? I return Z1 minus 500. That's it. It's the residual form. Residual form for parachutist hitting Z equal 500 meters, because they jumped from 1,000 meters, right? Now, do we want to stop integration? We can stop integration, and we say dot terminal equal true. Leave the other condition untouched. Okay? So now you come here and say solve IVP and IC, and then if you press Shift Tab, you see here events, none. Okay, so here you put events, and you just give it an array with the name of the events. Okay, hit 500 event. Okay, run it. You plot. Look at that. It only integrated until z equal 500. Right? You see it went from 1,000 to 500 and it stopped. And not only that, you can inspect the event. You can go to sol.tEvents. Here, tEvents. Okay, so if you plot that one, what happens? It gives you the time at which your events occurred. Here I have one event, and my first event occurred at 14.425 seconds. Okay? So that's when it hit. It took the parachutist 14 seconds to reach 500 meters. So we can do another event, let's say. Okay, so here I don't want it to terminate here. But then hit the ground event. Hit the ground. Now, Z1 is equal to 0, so I'm going to send Z1 minus 0, or simply Z1. Hitting Z equal 0. And this one, I want it to be terminal. Okay, so compute the event at 500, get me the time when it reached 500, but also get me the time when I reach 0 and stop there. Right? So run this, hit 500, and then hit the ground event. Run. Oh, looks like it stopped here. I see event. Pardon me? Oh, yeah. My bad. Thank you. Whew. Oh, thank God. Okay. Okay, so now I have two events. The first event, 14.42 seconds, is when I hit 500. So it's about what? Here, 14. It's when I hit what? 500. Oh, here, 500. Okay. And then it didn't terminate. It continued going until I hit the ground, and it stopped. This is great, right? And it didn't have to integrate. I can put TF 1,000 or 2,000. It will just stop, right? Stop where I want it to. Okay. We can do another event for speed. So there you have to do them one by one. So let's look at speed. Okay. plt.plot sol.t, and then speed is going to be sol.y1. Okay, so that's my speed. It's kind of going down. Okay, so let's see when we hit minus 20 and when we hit minus, let's say when we hit minus 20. Okay. Def speed event, whatever. So now my Z2. So residual form for parachutist hitting V equal minus 20 meters per second. So this implies V plus 20 is my residual form. Residual form. Okay? So Z2 plus 20. Now, if I put terminal is true for the speed event, it's probably going to hit that speed event before it hits any of the other events. So that would be a bad idea. Then I cannot hit the other events. So I'm going to put speed event, terminal is false. And then I'm going to put the speed event here. Actually, let's put it at the end. It doesn't matter the order. It's going to look at all of them. So let's run this. And then speed event. Okay, I run it. It's continued doing its thing. Now I have another value. This event when we hit Z500. This is the time when we hit Z equals 0. This is the time when we hit speed equal minus 20 meters per second. Really, really, really cool. In my numerical methods, with ODE int, I used to give this homework and say, find the time, or like the friction factor or something. Find the location of where the friction factor is this much. This takes the guesswork out of it. It embeds a nonlinear solver into this. It's a really good detection tool. Events. Okay, don't forget about it. And right on time. Okay. Thank you. Godspeed. I'll see you on Thursday.